Welcome to the video 2 of the series MOS amplifier common source configuration with resistive drain. And in the video 1 we already talked about how to solve problem 1, where we determine the bias or the DC bias or the quiescent condition, where we find the width of the MOS and also find the value of the resistor so that we can put our MOS in the appropriate operation region, which is the saturation region. If you have not watched the video, please watch it, since it's very practical in reality. In reality, whenever we start to analyze a amplifier circuit with a MOS, we always need to pay attention that we have to start from the DC bias condition analysis before we do the small signal analysis. In this video, we will do the small signal analysis. And first, if you have not known about the details or any concept about what does it mean small signal analysis, large signal analysis, please refer to the references that I put in the description section of this video, especially the reference where I put the link to the author Behzad Razavi. He explains very well about the small signal analysis in general. Please watch it out before you watch this video, because this video is only like a practice. And we start to do the practice, we will check our practice in simulation. And now let's go to the problem solving process. So we need to solve this problem, the small signal analysis of our MOS. Observe that we already solved the DC bias condition in the problem number 1. We need to find the circuit gain. So what does it mean, the circuit gain? So here we only see that there's the DC voltage to bias our MOS. There is really no small signal input, so let's assume that we have a small signal input here. Small signal input, simply sometimes we only want to mean that a variation signal with a very small amplitude, or we can give a very simple example like a sinusoid wave with a very small amplitude, so we call it small signal analysis, and that will be on top of the DC voltage that we already put in the circuit. And then we need to find the gain. We got the small signal here, and the output will have an amplifier signal, and we want to know the gain. So we want to know the ratio between the V out here over the V in here. The small signal input, we call it V in, and then there will be variation signal at the output, and we call it V out. And the ratio between the V out and the V in small signal is called the gain of the circuit. And also in our case, we will do it very simple. We will analyze the gain at low frequency, not high frequency. So because we have a variation signal, it means the variation signal can have frequency to be low or to be high. Low, it means like 10 Hertz or lower than 10 Hertz. And high means like 1000 or 100 kilohertz or something like that. So in our case, we just want to find the DC gain or low signal gain here. So that's our purpose today. The circuit gain, V out over V in at low frequency, DC gain of the circuit. Now let's move to the process, and in order to solve that problem we need to know two concepts. The first concept is the small signal model of the MOS when the MOS is biased in saturation region, and then we need to know about the Norton equivalence. And for the small signal model of the MOS in saturation region, I cut out the symbol of the Nmos here. Of course, here we can see that there's the bulb connected to the source, but in our symbol analysis we can neglect it. We only care about the drain, the gate, and the source. So this is the symbol model that we have for the MOS. What does it mean, model? Just a simple explanation. We have a physical device, and when we got the physical device, we will do the experiments in order to get some details about the parameters of the device. And we want to relate parameter every parameter of the device together through a formula or something, or through a model. And next, when the next step, if we want to use that device, usually we don't need to do the experiment again. We only need to use the abstract model that we constructed earlier to predict the maybe predict some parameters or predict some characteristics of the device itself, or approximate or calculate the characteristics of the device. And in our case, the simple small signal model of the MOS is also the same. So we have a Nmos is the physical device, and then they do experiments, they extract details about the characteristics of the MOS, and then they abstract it into an electrical model. And this is the electrical model of our MOS in the saturation region. And with this simple small signal model, we also neglect a lot of secondary effects like the channel length effect and the bulk effect. Of course, with those neglected information, our predicted or our calculation of the gain will be a little bit inaccurate. However, it won't be that much. The error might be less than 20%. So, in my opinion, it's acceptable. And it's the best way to approach with the concept when we first introduced to such a thing. Now let's see the model. We have the gate, of course, it corresponds to the gate. Source corresponds to the source, and the drain corresponds to the drain. And you need to know that the model also reflects how the symbol look like of the device. So in the symbol of the Nmos, we have the gate isolated. You can see there's the isolation or the separation between the gate and the rest of the device. And if we look at the model itself, we can see that the gate also got isolated from the drain and also from the source. This is an open and this is an open. Why I put the voltage here? It just means, of course, in our analysis we will put a voltage between the gate and the source. So I put the voltage here, but actually if I don't put any voltage here, the gate is isolated from the source and also isolated from the drain, just as is illustrated in the symbol. There's the isolation here. And what about the drain and the source? If you look in the symbol and follow my mouse tracing, you can see that the drain is connected to the source. And here you can even see that the drain connected to the source. But the connection is through a voltage control current source. Voltage control current source means it's a current source, but the value of the current is controlled by a voltage. And according to our model, this amplitude of the current is controlled by the difference between the gate and the source, or the gate source voltage in short. The formula here shows that this current ID, or the drain current, depends on the difference voltage between the gate and the source. In other words, the gate source voltage. And the direction of the drain current, if you look at the symbol, you can see there's an arrow directed from the drain to the source. So that's why in our model there's also the direction from the drain to the source. And next, for the formula to depict the relation between the value of the drain current and the gate source voltage, when I say about the drain current here and the gate source voltage here, we are talking about the small signal, not the large signal. So we can see that even the symbol for the ID or the VGS is quite different compared to the video one that we talk in the video one. Okay, next we talk about the parameter in this formula, GM. GM is called the transconductance, and the definition of the GM here, please refer to my references. Here I just extract the information. So the transconductance is equal to the differentiate of the drain current in respect to the gate source voltage. How can we do that differentiation? Of course, in the video one we also introduced this square law model, or the equation of the MOS when the MOS is in saturation. And this equation is the general equation, very general one. For large, for small, for DC analysis, we can always use this equation. That's why it's a general equation. And with this equation, we have the drain current here and we have the gate source voltage here. We can differentiate the drain current in respect to the gate source voltage, and we got the parameter transconductance. This definition over here is only to give the intuition or understanding about the transconductance, but in simulation we don't need to care about it, because when we already put the appropriate width and also the appropriate value for the resistor, and it means we put our MOS in the appropriate saturation region or the DC operating point already, we can run the simulation and then we can extract the value GM from the simulation when we don't need to do the differentiation to get the value. So that's the introduction about the simple small signal model of the MOS when the MOS is biased in the saturation at the appropriate DC operating point. And the second notion about the Norton equivalence, please, if you don't know about the details of the Norton equivalence or Thevenin equivalence, please refer to all the circuit theorems because they are very important. In this case, I just briefly go through what is the Norton equivalence. So like reminding. Usually we will have a circuit which we don't know anything about this circuit, but we want to know about the voltage between the two terminals of the circuit itself. Then how can we solve the problem? To solve this problem, they model this circuit by an equivalent circuit, and this such a equivalent circuit with the current and the parallel resistance. This equivalence is called Norton equivalence. And to calculate the V out between the two terminals of the circuit, we can see that we need to follow this formula. Why do we have the minus sign here? If you follow the direction of the current, you can see that the current flowing, sorry about my mouse, you can see that the current flowing through in this direction, going in this direction. It means that the current going through the resistor is from the lower voltage point, because I denoted by the minus sign. It means it's the lower voltage point to the higher voltage point. So the voltage drop on the resistor is IN times RN, but it's not the V out yet. So for the lower voltage point, because it's lower, so I can just reference this to be 0. 0 here doesn't mean that it's connected to the ground, but it's just a reference to say that it's 0. So if I want to know about the voltage over here, it would be like 0 minus the voltage drop on the resistor. So it would be 0 minus Rn times IN times Rn. So that's why we have the V out equal to minus point. One more note is that for the direction of the Norton current, it doesn't need to follow such a direction. You can put it in the opposite direction. I put it in this direction in order to get this formula. If you put in the other direction, the formula will be different, of course, but I will use this direction because it's related to our MOS analysis later on. And next, going back to our Norton equivalence, of course they model the unknown circuit with a model, and the parameters like the IN or the RN, they are also unknown. In order to determine their values, how can we determine them? First, to determine the IN, we need to short the output. We can see that I short the output here, and if we follow the current will go to the short rather than go to the resistance, because the short can be think of no resistance at all. So the current prefer the way where there is least resistance, which is the wire. And if we measure the current going through the wire here, we've got the IN itself. And next, to find the Rn, we need to put at the output a voltage source Vx, and when we put the voltage source Vx, we'll have a current going into our circuit. And another thing that we need to pay attention is when we got this kind of voltage put at the output, the existent sources should be replaced. The existent sources in this case is the In. It exists before we put this Vx, right? This is In inside our circuit. So if we need to replace it, what kind of replacement we should replace our In? So we can say that In should be 0. If In, the current is 0, so the current source itself is open. That's why the current is replaced by an open. So if after we replace all of the existing sources and we only consider the voltage source we put at the output, we can see that our Rn related to only the Vx and Ix through an Ohm law. We have Vx over Ix Ohm law equal to the resistance Rn. Sometimes we don't need to care about the value of the Vx and Ix, since we sometimes only need to know the expression of the Rn. Of course, in this model, Rn is only a resistor, so the expression is not that complicated. But when we start to do analysis with a more complex, for example, like the amplifier with the MOS in the common source configuration, the Rn is not that kind of simple to see. So next we will do the example. We will apply those two concepts. First is the small signal model of the MOS amplifier of the MOS in the saturation, and the second concept, Norton equivalence, to analyze or to calculate the circuit gain of our MOS amplifier with the common source configuration and resistive drain. And this is our analysis example for the circuit. The first step we need to do, we look into the circuit, we determine where is our MOS. This is our MOS, so we'll replace it with the small signal model. This is our MOS, replaced with the small signal model. The V in here, we assume that on top of the DC voltage, we have a small signal at the gate. And if we only care about the small signal, the VDC or the DC voltage can be looked at like a short. So it means the voltage between the source and the gate, because the source is connected to ground and this is also the ground, means they are connected to each other. And if the VDC is short, so the voltage between the gate and the source here is our small signal. We call it V in here. And the MOS itself in the small signal is replaced by a voltage control current source over here with the drain current, small drain current, equal to the small signal at the gate source times the transconductance Gm. And then we need to complete the whole circuit based with the small signal model replaced our MOS. So the rest of the circuit, we just need to pay attention to the resistor over here is this one, the resistor over here. And then the other terminal of the resistor is connected to a DC voltage. And because we are again looking into the small signal analysis, so for the DC voltage we can just consider it like a IC ground, just like we consider here. Here it's not like we consider like a ground, we consider the DC to be a short. But here we can consider it to be the ground. And the source, of course the source of the MOS is connected to the ground, so it's the ground here. So this is the whole small signal equivalence of the whole circuit, not only the MOS itself. So for the small signal model of the whole circuit, first we need to replace our MOS, and then we complete the rest of the circuit on top of the small signal model of our MOS to have the small signal model of the whole circuit. And after we got the whole model, we need to find here is the gain that we need to know, the gain at the low frequency. and the gain at the low frequency, as we introduced earlier, is equal to the V out over our V in, the ratio between V out and V in. We want to know how much the V in is amplified to be at the output V out. So we need to find this ratio, and in order to find this ratio, we need to use the Norton equivalence. So this is the Norton equivalence steps. So the first step for the Norton equivalence, we need to determine the IN. To determine the IN, we need to short the output, and when we short the output, we look into the circuit. What do we see? We can see that the drain current over here, will just circulate over there. It will go just like that. So it means IN equal to our drain current ID, and our drain current ID according to the small signal model of our MOS, it will be equal to V in times GM. And after we got the expression for IN, what do we need to determine? We need to determine the RN. So we can see the V out. Okay, for the IN, how do we determine the RN? As we say in the Norton equivalence introduction, we need to put at the output a voltage source Vx. When we put a voltage source Vx at the output, we have a current Ix going into our circuit, and all the sources inside our circuit need to be zero. It's somehow quite similar to how we solve a circuit with many sources with superposition if the circuit is a linear circuit. One note is that we can, for the control source, the source which is dependent on another value or another parameter, we cannot just put them to be zero. We need to properly investigate them. However, we can put our V in to be zero because our V in is a totally independent source, so we put V in equal to 0. And if V in equal to 0, because of the relation V ID equal to V in times GM, that's why we know that our ID in this case is also 0. If our ID in this case is 0, it means our voltage control current source is open. If it's open, what does it mean? It means our Ix current can only go through this R resistance and go to the ground. So if we take the ratio between Vx and Ix, we will say that the Rn equal to Vx over Ix equal to the R, the resistor R here over here. And according to the Norton's equivalent, what do we see? That for the V out, with this direction of the Norton equivalent, with this direction of the Norton equivalent, or with the source ground here, we can say that the V out equal to minus In times Rn, just like we say earlier. And we replace everything, and we got finally the expression for the gain at the low frequency, the ratio between our output voltage over the input voltage. Usually when we analyze the gain, we don't really analyze directly the value of the gain, but we will convert it to dB. So to convert to the dB, we will take this formula where we have 20 times log 10 amplitude of the gain. We will see this value. We will know that, okay, the gain of the circuit at low frequency is this expression, is this value. And for the GM, when we already biased our circuit in appropriate DC bias operating point, we can extract it from the simulation. We don't really need to differentiate it. And for the value of the resistor R, of course, it's already determined, so everything will be determined when we simulate our circuit. And we will check this one in the simulation of the cadence. I think the video is already long, so I'll put the simulation in the next video. So see you. Wait for the simulation to check this current gain in cadence.